Hi everyone. So in today's class, we are going to solve or work out some of the problems related to the conduction mode of heat transfer. So these are some of the questions that will encompass the thermal conductivity portion, the basics of conduction, and with this we will be doing a few questions that will help to garnish your fundamentals that we have studied. So let's start with an example, a problem that encompasses all the fundamentals of the thermal conductivity part. Okay, so I will try to dictate the question over here. Okay, so the question is that supposing if a layer of 5 centimeter thick insulating brick having conductivity of 1.5 watt per meter Kelvin is placed between two 0.5 centimeter thick steel plates. So a layer of 5 centimeter thick. So the thickness is 5 centimeter and it is a brick. Given its thermal conductivity is 1.5 watt per meter Kelvin. This is placed in between two 0.5 centimeter thick steel plates. This is placed in between two 0.5 centimeter steel plates having thermal conductivity of 50 watt per meter Kelvin. Fine. Then the faces of brick adjacent to plate are rough, having solid to solid contact of 30%. Means the contact resistance concept is coming into picture, and it says that the face of the brick that is in touch with this SS plate, what does it shows? It shows it has a roughness, and the roughness is such that there is plate to plate 30% of contact. That means rest 70% is contacted by air, isn't it? So if 30 plate to plate is says the faces of brick adjacent to the plate are rough, having solid to solid contact of 30%. If the solid to solid contact is 30%, that means the rest void that is remaining, it will constitute the air that encompasses the 70% of the net area. The average height of the asperities is 0.1 cm. So it says that the thickness over here is suppose 0.1 centimeter. Then if the outer plate surface is at temperature of 100 degree and 500 degrees Celsius, suppose this plate is at 500 degrees Celsius and this plate is at 100 degrees Celsius, then calculate the heat flux. Then what will be the heat flux with K of air that has been 0.02 watt per meter Kelvin. So here, so all the things that has been given is that a brick is there that is attached with two plates, and the plate to plate contact shows here 30% of the solid to solid contact, and rest 70% is the contact because of the air. So the thickness over the asperities is 0.1 centimeter and the thermal conductivity of air is 0.02 watt per meter Kelvin. So here we have to find out what the heat flux is. Then we know that heat flux can be given by T1 minus T2 by RTH. This we have discussed, isn't it? So now we have to calculate the total thermal resistance. So what will be the total thermal resistance? The total thermal resistance will be the thermal resistance offered by the brick RSS plus R as means because of this contact resistance, R contact resistance, then resistance due to the brick, then again R contact resistance, then resistance due to the SS plate. Then again this R contact resistance is because of the R plate to plate or solid to solid plus R air. This plate to plate constitute of 30% and this air it constitutes of 70%, isn't it? Then we have to find it one by one. You can easily calculate the RAS and R brick. What will be the R? The R will be L by Ka. As it is asking the heat flux, so we can consider the area to be a unit one and we can directly write here as the L by Ka for this SS. It will be 0.5 into 10 to the power minus 2 by 50 into 2, that is 2 into 0.5 into 10 to the power minus 2 by 50. Similarly for brick it will be 1.5 into 10 to the power minus 2. It will be 5 into 10 to the power minus 2 by 1.5, isn't it? This will be for the R brick. Now comes the R air. Similarly for solid to solid, it comprises 30% of the solid area. That means L by Ka. So this will be 0.1 into 10 to the power minus 2 divided by the solid to solid contact is over here. Then what is the solid to solid? It is the brick to steel contact, isn't it? So for the brick to steel contact, what will be the thermal conductivity over here? So here the solid to solid contact, the thermal conductivity will be 1.5. Here it is 1.5. Suppose here the brick, the means the protrusions, it will be having 50 watt per meter Kelvin, and let us assuming that the effective thermal conductivity of the solid to solid contact that is happening over here is 1.5 into 0.3 of area. Similarly for air it will be 0.1 into 10 to the power minus 2 divided by 0.02 into 0.7. So you got all the thermal conductivity, this thermal contact resistances. Then you got the resistance for this solid to solid contact and air. Then you have to calculate the equivalent contact resistance. So the resistance equivalent, this is equals to R1 into R2 by R1 plus R2. So we have here R1, R2. So R1 into R2 by R1 plus R2. And this overall thing, this thing by using this formula, you can calculate the net heat flux, isn't it? So hope this is made clear to you. If here, why we have considered 1.5, here the 1.5 is the reason is that the brick surface is having protrusions and the big brick is being brought to in contact with the SS plate. So as the contact is there, so we consider that the brick contact thermal conductivity is 1.5 watt per meter Kelvin. So here you can write assuming what I stated now, as most of the portions of the brick is basically it's a porous kind of thing. So the more surface roughness will be observed in the brick itself. So brick means considering the thermal conductivity of brick to estimate the contact resistance of solid to solid, we estimated this thing. We can write it over here. So this is the way how to solve this problem. Fine. Now we will move on to solving our first problem that has been asked in our GATE examination, and the problem is two insulating material of thermal conductivity K and 2K are available for lagging a pipe carrying a hot fluid. If the radial thickness of each material is same, then material with higher thermal conductivity should be used for inner layer with the one with the lower thermal conductivity with the outer. Material with lower thermal conductivity should be used for inner layer and one with the higher thermal conductivity for the outer. If it is immaterial which sequence the insulating material are used, and it is not possible to judge unless numerical values of the dimensions are given. So if we will see over here, I will try to make this problem understanding to you all. So here the thing is that it is telling here, the thing is that it is telling for two insulating material the thermal conductivity are K and 2K. So let's go and start drawing this. So it is a pipe. Okay, pipe is given. Suppose this is the first thickness, this is the second thickness, R1, R2 and R3. Here the thermal conductivity be K, here the thermal conductivity be 2K. Now let us consider another case as it is being given over here, R1, R2, R3. Suppose this is 2K and this is K. So it is asking that two insulating material of thermal conductivity K and 2K are available for lagging a pipe carrying a hot fluid. If the radial thickness of each material is same, that means the thickness, this thickness and this thickness are same. That means R2 minus R1 is equals to R3 minus R2. This condition is given to you. Okay, R3 minus R1 equals to R2 minus R1 is equals to R3 minus R2. Okay, as this condition is given, and it is asking which thermal conductivity to be kept in the inside material and outside. Supposing if I have taken in the first case that the lower thermal conductivity is kept inside, then the higher thermal conductivity. In the second case, I have kept the higher thermal conductivity inside and lower thermal conductivity outside. So which one is proper or the correct arrangement to keep this into mind? So here, as two thermal conductivities are there, then the heat flux that can be given by delta T divided by ln R2 by R1 divided by 2 pi Lk plus ln R3 by R2 divided by 2 pi Lk, isn't it? So here 2 pi Lk we can take it common and we will just make it out of the system, and here K, here one side here it will be K and in the other side it will be of 2K. So if it is K and 2K, then delta T, let us consider this first one. So here R1 R2 by R1 by 2 pi Lk plus R3 by R2 by 2 pi L into 2K. So this will be ln R2 by R1 by 2 pi Lk plus ln R3 by R2 by 4 pi Lk. So let's take the common, let us take the common out over here, delta T divided by 1 by 4 pi Lk, then it will be 2 ln R2 by R1 plus ln R3 by R2. So this factor, this I can simply write it as R2 square by R1 into ln R2 square into R3 by R1 square into R2. So R2 get cancelled. So this will be ln R2 R3 by R1 square into this factor delta T divided by 1 by 4 pi K. So this will be equals to delta T divided by ln 1 by 4 pi Lk will take common ln R3 R2 by R1 square, isn't it? This thing will come into picture. Then let's calculate for this part, that is for R1 by R2 it is 2K and here it is normal K. So here let's multiply 2 and let's delete the factor here. Then it will be R2 by R1 by 4 pi Lk and R3 by R2 by 2 pi Lk. Now taking 1 by 4 pi Lk common, this will be ln R3 by, this will be ln R2 by R1 plus 2 ln R3 by R2, then ln R3 into R2 into R3 square divided by R1 into R2 square, R1 into R2 square. So this will get cancelled. So this will become ln R3 square divided by R1 R2. Now here in the denominator everything is same, delta t same, 1 by 4 pi lk is same. So the denominator is ln R3 R2 by R1 square, and here it is ln R3 square by R1 R2. So this is the deciding factor which will decide. And if you will see here, we know that R2 minus R1 is equals to R3 minus R2. Okay, that means this thickness R2, this thickness is equals to this thickness, the radial thickness is same, of each material is same. Then by substituting the value, you will see that the configuration, that is this factor, the overall heat transfer will be less. For what? For this factor when it will be more. So this denominator factor is more for the case where the thermal conductivity is lower at the inner side. This is because you substitute, you equate this equation, then it will be 2R2 is equals to R3 minus R1. Then R2 is equals to R3 minus R1 by 2. So R2 equals to R3 minus R1 by 2. Substitute the value, try to solve it out. You will get that the material with which the thermal conductivity should be is low is used for the inner layer, and with the higher thermal conductivity will be used for the outer layer. Hope you got it. And always remember if you, it is a 1 mark question and you don't want to calculate so much, this is a derivation. You can see in this way we can go and work it out. If you don't want to work it out, what you can do is that you can simply take the thermal conductivity K and 2K, and you see if the inner side the thermal conductivity is small, lesser the thermal conductivity, less heat will get transferred. What much lesser heat will get transferred, then again if a higher thermal conductivity is used, then no matter what will be the magnitude of the thermal conductivity, lesser heat will get conducted, because already resistance has been offered by this lower thermal conductivity area. However, if there is a higher thermal conductivity material, then more amount of heat will get passed through that. So irrespective of having the smaller K, more heat as compared to here will get out of the system. That's why for a material to insulate its property, if we are having differing insulating material, then the material with lower thermal conductivity should be insulated in the first case, then we should move for the second case. Hope this question is clear to you. Now moving on to another question. So the question is, if the temperature variation under the steady state conduction of a composite slab is such a way that is K1, K2, then which of the following is same? K1 greater than K2, K1 equals to K2, K1 equals to 0, K1 less than K2. Remember, while studying the thermal conductivity, you have studied and proved that greater the slope, lesser is the thermal conductivity. So here slope is higher for this K2 as compared to K1, isn't it? That means K1 is greater than K2. The first case, K1 is greater than K2. Now we will be moving on to another problem, and the problem states that in a composite slab, the temperature at the interface is T inter between two material is equals to the average of the temperature as the two end. Assuming steady state one-dimensional heat conduction, which of the following statement is same? What does it states? It states that T inter, supposing here temperature is T1 and temperature is T2, T inter is equals to T1 plus T2 by 2. Then it is asking which of the thermal conductivity is same. That means the Q heat flux will be T1 minus T inter divided by L by K. So 2B by K1 is equals to T inter minus T2 divided by B by K2. This implies, if we will see what will happen over here, we have to find an equation between this K1 and K2. Let's make this T1 minus T inter by T inter minus T2 is equals to 2B by K1 divided by B by K2, isn't it? So this thing I can write it to be T1 minus T inter, that is T1 plus T2 by 2 minus T1 minus T2 by 2 divided by T1 plus T2 by 2 minus T2. So let's this denominator, this will equals to T1 minus T1 minus T2 divided by 2 by T1 minus T2, T1 minus T2, this will be T1 minus T2, and this will be T1 minus T2 by 2. So this overall thing will get cancelled. This implies, so 2B by K1 equals to B by 2B by K1 is equals to B by K2. Then B get cancel. This implies 2K2 is equals to K1. So what will be 2K2 is equals to K1. Hence proved. Now let us move on to another question. And what does the question states? Consider a one-dimensional steady-state heat conduction without heat generation in a plane wall. The boundary condition is that your K is equals to K0 plus B into T, and given that K0 and B are positive, and it says that T is the temperature. If T2 is greater than T1, what will happen over here? Here K0 and B are positive. Then as T increases, K will give you a positive value. Why? K0 and B are positive. So as T increases, K also increases. Then Q is equals to minus K dt by dx. So as temperature increases, the thermal conductivity also increases. So this thing dt by dx, what will happen? It will tend to decrease, isn't it? Because of the negative sign. Because as thermal conductivity increases, this is T1, this is T2, then what will be? The slope will tend to decrease. Now moving on towards the another question. So it states that a slab is there, thermal conductivity K, 2K, both the thickness are same, which is L and L, to temperature 600 and 300. So the interface temperature, it is asking what will be the Ti. So what will be Ti? Then we have just solved the problem as before. It is another category of that. The heat flux is equals to 600 minus Ti by L by K. This is equals to Ti minus 300 by L by 2K. This implies let it get cancelled, 1 by 2, then this will get multiplied 2, and this 600 minus Ti is equals to 2 Ti so 600 minus Ti, sorry, I did a blunder over here as a, so 600 minus Ti, 600 minus Ti by K equals to Ti minus 300 by, this will be L by 2K, isn't it? So what can I write over here? This L by K and L by 2K. So 600 minus Ti is equals to Ti minus 300 divided by L by 2K into L by K. So L by K, and here it will be, so if it is double, so this will be somewhat the average, that will be around, if we will take K get cancelled, the LL, then this will be 2. So then you can see what will happen over here. So this implies the Ti here, what will be the value? Try to solve it and let me know. Okay, that what you are going to get the value of T. So if you will see over here, what will be the value of T that you will be getting? So we will be getting the value of T as what will be this TAI? K get cancelled, LL, this 2 will get up. Then what we can write over here? So what can we write over here? 600 minus Ti is equals to 2Ti minus 600. This implies 3Ti is equals to 1200 and Ti is equals to 400 Kelvin. So you get the value of Ti over here. Hope you are clear with that. Now we will move on to another question. So what does it says? It says that for a steady one-dimensional heat conduction takes place across the phase 1 and 3 is perfect contact in the figure where K and Kb denote the thermal conductivity, and we have to calculate the interface temperature. 2. The same question like we solved, just see how you are going to solve it. This means T1 minus T2 by 0.1 by 20 is equals to T2 minus T3 by 0.3 by 100. So try to calculate the value of T2 and try it's simple mathematics, try to solve it and get back. So this question is done. Now we will move on to another question. What does it stress? That heat is generated uniformly in a long cylindrical rod at the rate of 4 this much. The thermal conductivity is this. Under the steady state condition, what the temperature difference between the center and surface of the rod is. So you have to calculate that at the steady state condition, what is the temperature going to be. So here what factor comes into the picture? The factor that come into the picture is the temperature. So how or in which way it is going to get effect over here? So here you know that for a cylindrical rod, if it has been given and it is given a steady state case, so what is the formula for the heat generation? We know that T0 minus Ts is equals to Q dot R square by 4K for a cylinder. So T0 minus T surface, what we know? T0 minus T surface equals to Q dot R square by 4K. Q dot is given, diameter is given, K is given. You try to solve this question. So hope you got this question right. It is a simple direct application of the heat generation portion that we have been discussing. So it is Q dot R square by 4K, and hope you were clear with what we have studied. Now moving on to another question. So what does it says here? That a plane slab, this side the H is 10, T infinity is 45 degrees Celsius, and here the surface is 25 degrees Celsius, and the plane slab of thickness L and thermal conductivity K is heated when the fluid on one side and other side Q is maintained at a constant temperature of 25 degrees Celsius. The fluid is at 45 degrees Celsius and the surface heat transfer constant is 10 watt per meter square Kelvin. It is a steady state and it is asking to find the temperature Tp from the side with which it is exposed to the fluid. So it is asking Tp. Then this Q is heat flux, that is equals to Q convected is equals to Q conducted. That means H into T infinity minus Tp is equals to Tp minus Tq by 20 centimeter, 20 into 10 to the power minus 2 L by K, 2.5. So here T infinity is given to be 45 degree. TQ is equals to 25 degrees Celsius, 25 degrees Celsius. Then you can calculate the value of Tp is equals to dash degree Celsius and try to solve this question. Hope with this you are okay with all the thermal conductivity related fundamental problems of heat conduction, and we will try to solve most of the more problems as per this, and we will try. So with this we are concluded with all the basic fundamental questions that according to the thermal conductivity can come. Apart from such categories, there are no more questions in which the thermal conductivity application can be formed. So in the next class, we will try to solve out some of more steady state heat conduction problems along with the unsteady state heat conduction problems and fins. So hope what much we have discussed today you are clear. Try to work it out by your own, and in the next class we'll start with the remaining of the steady state heat conduction and along with the unsteady state heat conduction, and in next class we will be completing the GATE previous year questions of this heat transfer conduction mode of heat transfer. So hope this class was informative to you. Thank you and have a good day.